In this lesson, we're going to be expanding our look at vectors, and we want to extend into three-dimensional space. But to do that, we have to make sure that we've wrapped up all of the things we need to talk about in two-dimensional space. Two-dimensional space, from an abbreviation point of view, is often referred to as R2. And when we think of two-dimensional space, we're talking about a flat surface, for example, a flat piece of paper, or the flatness of this screen and how we're representing things. We have typically, you should be completely familiar with the Cartesian plane because you've done all of your work with the Cartesian plane for the majority of your high school career. And so that's where we have the x-axis and the y-axis. The x-axis and y-axis are oriented at 90-degree angles to each other. And we can take any point and represent it in terms of its x and y coordinates. So for example, here I've chosen the point 3, 5. So I counted off 3 in the x direction and 5 in the y direction. That gave me that point. I could also represent that point and its location in terms of a vector, rather than the idea of counting 3 horizontally and 5 vertically. I could just say, okay, well, it's some distance. It is some distance away from the origin, and the origin is always at 0, 0. So it's some distance away from the origin at some angle, for example, some angle theta. I could do it that way. And that would still get me as a path, that would get me to that same point. Now, something I want to point out to you, which is when we talked about the point itself, it had coordinates 3, 5. And you're very familiar with this notation, which is just the Cartesian coordinates x, y. But notice that I've represented this vector which goes from the origin O to the point P as the vector OP. And notice that the vector OP also uses this round bracket notation 3, 5. So in many ways it's indistinguishable from the point, especially if you didn't have this letter P in front of the point. So the thing I want to bring to your attention right away, and something you just need to reinforce constantly, you've run into this idea already with different types of math, which is context matters. And what I mean by that is you have to recognize what you are looking at, what the information is that you're being given, depending on the context, depending on the situation. So in this case, I have OP with a vector symbol, and I'm saying that's equal to 3, 5. Well, that means that this is a direction vector. You have to understand that context. If you were given something like this, P bracket 3, 5, you have to know that's not referring to a vector, that's referring to a point. And then to make matters even more complicated, we have the situation where we actually describe the position of a point using a position vector, and they both have very similar or identical looking notations. Now, another way that we could think about this would actually to be going back to that idea of counting out. As I said before, how did I find my original point? I counted 3 to the right and then 5 up. We can do that in a similar way using a vector notation. And in this case, instead of the idea of just counting 3 to the right in terms of coordinates, I imagine a position vector which would move me 3 steps to the right. So that's this green arrow. And then I have another position vector which would, or not a position vector, just a vector. So I have a vector that would move me 3 steps to the right. I have a vector that would move me 5 steps up. And these two vectors, if I combine them using vector addition, so if I were to put them, oh, that's not going to work. If I were to put this tip to tail, and I add that red vector to the tip of the green vector, then you can see I end up with my vector OP. So the vector OP can be represented as a vector sum, adding these two vectors together. I also want to point out something in notation here. Sometimes it's kind of awkward to include a vector symbol. In my case, when I'm preparing these notes, there's no ready facility to allow me to put these vector arrows on the top of these. It takes quite a bit of extra processing. I have to create other things in the equation editor, and that's actually a fairly common problem. So a convention that is sometimes used is when you see something like this in bold, it's basically saying, I understand that from a word processing point of view, this is not ideal, but it is a concession that we make to being able to do things in a reasonable amount of time. And so OP and A and B are in bold in this text, and that means they are referring to the vector OP, the vector A, and the vector B. So that's just something for you to keep in mind. Now this vector A, how would I actually describe that vector A? If I had to describe that vector A represents a movement of 3 to the right, or 3 in the x direction, and no movement upwards, which is 0 in the y direction. The vector B, on the other hand, represents no movement in the x direction, but actually represents 5 steps in the positive y direction. So when I say the vector OP is the vector sum of these two vectors, then what I'm actually saying is OP is A plus B, which is 3, 0 plus 0, 5. And when you add these, when we perform this vector sum, so when we perform this vector sum, what we're doing is we are adding these things called component vectors. So this one is my x component vector, and this one is my y component vector. Now, those of you who have a background where you've dealt with vector components before will find this probably familiar, but not entirely familiar. It won't be the same way that you've done them in the past. But hopefully you can see the connection between them, and we're going to go further with this. We'll talk further about this idea of these components. But for now, we're basically taking the simplest approach. We're starting with fairly simple vectors to start with, and the components are quite obvious because the components come from the x part and the y part of the vector. So if you're looking to capture something in your notes, this is what I would suggest. It's a condensation of what I was going through before, just kind of really sticking to the relevant information. So we're talking about R2, which is a two-dimensional plane. And typically that's going to be our XY plane. So we're going to have the x-axis and we're going to have the y-axis, and that forms a plane, that forms a flat surface, and we call that R2. So we can take any point in R2 and we can locate it in terms of a position vector. And that position vector is going to have a form that is indistinguishable from the coordinates we use to describe that point. So you have to remember context. The length of that vector is found using the distance formula essentially, and it's just Pythagorean's theorem. We have a right triangle here. So if I were to drop that down, this is a y value and this is an x value, and the length of this hypotenuse is given by the square root of x squared plus y squared. We can also represent any vector in R2 using component vectors, which means I basically take my vector and I break it up into a piece that lies entirely along the x-axis and a piece that lies entirely along the y-axis. It could also be, of course, along the negative x or the negative y. I'm just using positive x and y because it's convenient and easier to visualize. If you have the vector, you can break it up into its component vectors. If you have the component vectors, you can combine them together to find your final vector. And as you go forward, you can deal with multiple component vectors. So you might have many components along the x-axis and you have to add their x coordinates or their x values together. You might have multiple y component vectors and you have to add those y values together. So let's look at an example here. So here I am given two vectors. U is negative 3, 2, and V is negative 4, 1. The first thing I want to do is write each vector in terms of its vector components. So let's go to part A, and I'm going to rewrite U. So let's go ahead and rewrite the vector as it was given. And this is not a difficult thing to do. If I'm going to write this in terms of its vector components, I'm just going to write the component that lies along the x-axis is the -3, and the component that lies along the y-axis, oh, I apologize, I just put an extra bracket in there because I've got three-dimensional space on my mind. So the -3 lies along the x direction, the 2 lies along the y direction. If I take the vector v, then I have -4, -1, and the -4 lies along the x direction, and the 1, or the -1, lies entirely along the y direction. This is going to seem very strange to you for a little while at least, because you're going to be looking at these things and you're going to be seeing points, and you're going to have to keep reminding yourself that these actually have another meaning, which is vectors. Then I say to determine the vector sum both graphically and using vector addition. Now, in doing this graphically, it's actually more difficult to do it graphically, especially if you don't have technology, if you don't have something like this where you can create straight lines, perfect straight lines. You could do this with a ruler if you were really careful about both your scale and your straight lines. So let's go ahead and put on -3, 2. So -1, -2, -3, +2, 1, 2. So that puts a point there. And then I can draw the vector to that point. It's going to look like that. And then I take another point, which is -4, -1, -1, 2, 3, 4, -1. And I'm going to draw the vector, the position vector, from the origin to there. Now, I've actually been asked to do the sum, the vector sum, so I'm going to add them together. But the way I need to do that, the way I have to add them together, is I actually need to take this vector and add it to the other one. So I'm going to go tip to tail, and because of technology, I actually have this option. But even with technology, I can see that I'm having to fiddle with this a little bit so that I end up where I'm supposed to, which is right here, and that's going to be my resultant vector, which is the vector that's formed from that addition. So we end up with that. Now, this was with a perfect grid using a line generation tool, and I still had to kind of fiddle around with it a little bit, and I knew I was dealing with integers. I already knew what my answer was supposed to be. If, on the other hand, you use vector components in this case and do this algebraically, then we end up with u plus v, which is equal to -3, 2 plus -4, -1. Now, I wouldn't necessarily recommend you go to this step, but I'm going to show it anyway, which is I'm actually going to break them into their vector components. Once you get good at this, this step will probably be unnecessary for you. So that's the first pair of vector components, and I'm adding to that the second pair of vector components. And when I add those together, what we end up with, the combination that we end up with, is this is an x component and this is an x component. This is a y component and this is a y component. So when I combine those together, I take a look at my x components. I have a -3 and a -4, and I'm adding them. -3 plus -4 gives me a -7. So that's my x component, plus a 0 and a 2 and a 0 and a -1. So that means I'm going to, the x part stays 0. 2 minus 1 is just equal to 1. And then I combine that into a single vector, and that becomes -7, 1. And if we go back and refer to our original diagram, -7, +1, that is the resulting point for that vector. Okay, so that's it for this lesson. Now, I say here I don't have any assigned work, and I tell you to see the web page. It's because this section of the textbook deals primarily with vectors in three-dimensional space in R3, and that's going to be the next video lesson. So you should see the web page to see which questions I'm specifically directing you to for this lesson and which ones tie into the lesson on three-dimensional vectors.